Okay, so welcome everyone to our first hybrid meeting of the Tutte Colloquium. Today we have Bousquet-Melou, who's a directrice of research at CNRS at the University of Bordeaux, where she also completed her PhD. Mireille has published many landmark papers in enumeration of different combinatorial objects in the study of combinatorial sequences. She received the silver medal from the CNRS and gave an invited talk at the International Congress of Mathematics in the combinatorics section. And I'm particularly excited to have her for the Tutte Colloquium because a lot of her research can be seen as sort of modern work building on what Tutte did 50 years ago. But today she'll be telling us about counting colored planar maps 50 years after William Tutte. So please go ahead, Mireille.
Okay, thank you, Steve, and thank you for inviting me to this Tutte Colloquium. I am especially enthusiastic about giving a talk there because at this place where Tutte lived and worked, and at a colloquium that bears his name, because a lot of my work, as you said, has been directly influenced by, in fact, a series of papers that Tutte wrote on the enumeration of colored planar maps. And this will be the topic today as well. So as Steve mentioned, so you can feel free to ask questions also during the colloquium. I will feel less lonely in front of my table. And also I want to apologize to those of you who are already familiar with maybe, I don't know, the first half of my talk, but I don't want to lose people early. So, well, you have to stand my basic definitions. So I will start by defining the main objects, that is maps, and also some simpler maps, namely trees. So this is a tree. So as we all know, it's a connected graph, which has no cycle. And you see my vertices are not labeled. And this tree is a plane tree, which means that it is given with one of its proper embeddings in the plane. So I don't want edges to cross. And two plane trees, that is two embeddings, are said to be the same if you obtain one by just a continuous deformation of the other that does not create edge crossings. For instance, here this is the same plane tree. I've just played a little bit with the top edge and moved a little bit to the left this vertex. They are the same plane tree. On the other hand, if I take this edge here and move it so that it crosses this one and ends up being these two edges like this, the plane tree that I get is different. So there's really this idea of embedding trees in the plane. So when people count things, or most people who count things hate having objects which may have symmetries, and trees may have symmetries. And so this is why we tend to focus on rooted trees, which are defined by just rooting or choosing one corner that's an angle between two edges that are incident to the same vertex, like here. And this, of course, defines a root vertex and also a root edge, the one that follows the corner in some say counterclockwise order here. And then we can draw the tree by hanging it at its root corner, and we get a picture that's probably more familiar to many of you. So much for trees. Now, what are these maps that Tutte loved to count? Well, they are also graphs in which we allow loops and we allow multiple edges, as you can see. They have to be connected, planar, and again, they are given with one of their proper embeddings, and two maps are equivalent if you can deform one continuously into the other. So these maps, well, of course, they have, as graphs themselves, they have vertices of various degrees. So for instance, this vertex here has degree 5, so the loop counts twice. And they also have something that graphs would not have when they are not embedded, namely faces. So here you have a pink face of degree 3 meaning that so the degree is the length of the walk that you can do around the face. So here 3. And there's one special face, which is the outer face, the one around the map. Now we will also systematically route planar maps by choosing one corner in this outer face. So here I would have 6 different ways of routing this map. And again, this defines a root vertex, a root edge, and this outer face I sometimes call the root face. And its degree is called the outer degree. So here it's 1, 2, 3, 4, 5, and 6. Okay. And so that's for maps. And now we want to color maps. So we have a set of colors. Say the number of colors will be denoted Q in my talk. And you color vertices as you wish. And certain coloring are called proper, which means that for every edge, the 2 endpoints have different colors. So this coloring here is proper. You can check every edge. And this one is not proper because here you have one edge whose endpoints have the same color. So I will say that this edge is monochromatic. But we want to consider as well these non-proper colorings. Okay, so as I said, so Tutte was the first one, I think, to get interested in planar maps in the early 60s. At that time, I think he was in Toronto, not yet in Waterloo. And since then, the topic has spread in various communities and sometimes independently. So here is now a list of fields in which one may meet and play with maps. So of course there's combinatorics. There's probability theory. For about 15 to 20 years, certain probabilists have started to get interested in the behavior of large random maps. Then before that, in the 70s, maps emerged completely independently in some part of theoretical physics as a model for quantum gravity. And then you can find maps in certain algebraic problems and also in computer science. And I may have forgotten some topics. So here is a rather brutal chronology of planar maps. So at the beginning was Tutte on this layer, who developed certain recursive approaches to count them. He wanted to know how many planar maps you can draw with the n edges, typically. And then came physicists using different techniques based on matrix integrals to count maps, and apparently they didn't know of Tutte's work. And then in the 80s and much more after the 90s, some people designed very nice bijections between maps and certain families of trees in order to explain in a very combinatorial fashion certain formulae that Tutte had obtained for the number of maps of this and that type. Because these formulae, as you will see, they resemble formulae for numbers of trees. So there should be a link, which is now established through bijections. And finally, these bijections, which essentially transform maps into trees, open the way to the probabilistic study of maps, because it's much easier to understand trees. So this is how things started in probability theory. But as I said, today I will just focus on, in fact, what I know the best, that is playing with recursive decompositions of maps and the corresponding recurrence relations and functional equations. So let's start à la Tutte, as we say in French, with recursive descriptions for counting maps. And again, I start with my favorite trees. So we take a rooted tree and we would like to count these objects, that is to know how many trees with n edges you can draw. And the best idea to describe them recursively is to delete this root edge. And you get two trees, one to the left, one to the right, and you can go backwards in a unique way. So here is the same decomposition in a more schematic way. So here, every little blue bubble here stands for a tree. I delete the root edge and I get an ordered pair of trees. So now we can move from recursive descriptions to recurrence relations. So if we let A of n be the number of these rooted plane trees with n edges, then we have some initial condition. There's just one tree with no edge. It's reduced to a vertex. And then this recursion tells you that a tree of size n, that is with n edges, is obtained by gluing a tree of size I, a tree of size j, so these are these two bubbles, provided I plus j is n minus 1. Okay, so we already have a recurrence relation, but we won't stop here. In order to solve it, we will introduce a very ubiquitous tool in combinatorial enumeration, namely the corresponding generating function. So that's a formal power series in one variable t. But the t will always denote the size variable in my counting problems. And the nth coefficient of this series is the number a of n. So alternatively, you can write this series as a sum over all plane trees of t to the number of edges of the tree. And then if you sit down for a minute, then you will soon convert this recurrence relation into a certain functional equation for the series. Well, you can essentially recognize this quadratic structure of trees. Okay, and now this equation, obviously, it can be solved very easily. So here is the generating function of trees. It has a nice expansion. So this modified binomial number is called the nth Catalan number, and it's the number of plane trees with n edges. Okay, so this is well known and understood. Now question, can we do the same thing with planar maps? Well, so we want to follow the same recipe, that is delete the root edge. And there you soon realize that there are now two different cases. Maybe the root edge here is what is called an isthmus, like in geography. And then when you delete the map, you'll get two maps, one to the left, to the right. And otherwise, for instance, here, if I delete this edge, I get a single map. So we have these two cases, which I have schematized here. So to the left, so now every blue bubble is no longer a tree, but a map. So to the left, you have the isthmus case, where when you delete the edge, you get two maps, and you can go backwards in a canonical way. And to the right, we have a more interesting case, where we delete the edge, and there's just one map that's left, not two. The problem is that if you just look at this smaller map, say with n-1 edges, you cannot reconstruct in a canonical way the bigger map. Because the root edge that you have deleted could have been maybe here, a little loop here, or maybe here. And in fact, what happens is that if the smaller map has outer degree d, so here it has degree 1, 2, 3, it is obtained from d plus 1 different maps of size n by deletion of the root edge. And here I've drawn the root edges of the four maps that project to this one. Okay, so can we use that to count maps with n edges? Well, these little pictures tell you that if B of n is the number of such maps, well, B of n is the sum of two terms, one corresponding to this tree-like case where we recognize the convolution that we had before, and one which is a sum over all possible outer degrees of number of maps of outer degree d and size n-1 times d plus 1, this multiplicity here. So this is nice and well, but this doesn't allow you to compute these numbers b of n, because here you have a refinement of your sequence. So really what this tells you is that if you want to use this recursive description of maps to count them, you need to refine your counting problem by considering this now array of numbers, b and e, the number of maps with n edges and outer degree e. So now if you agree to do that, you can indeed use this recursive description, and you will end up with this recurrence relation for this array of numbers. Okay, so this is typical of what happens with maps, at least if you use those naive decompositions, that you'll be forced to introduce a new parameter even if you're not very interested in it. So here is again this recurrence relation, and now we'll follow the same recipe as for trees. That is, we'll put these numbers in a formal power series, which now depends on two variables. So we still have the variable t recording the size, that's the number of edges, and we have an additional variable x recording the degree of the root face, the outer degree. And then again, you sit this time for 2 minutes, and you'll be able to convert this recurrence relation into a functional equation, which is here. So my series B is 1 plus a quadratic term. This looks like 3. And then this is the terms that comes from the case where the root edge is not an isthmus. And you see it involves divided difference, xb of x minus b of 1 minus x minus 1, which is typical in map counting. And I tend to sometimes to call this a discrete differential equation because of this divided difference. And this equation was written for the first time, of course, by Tutte, as many things that you will see in my slides. Okay. Now, before I move to the next problem, which is counting colored maps, I want to tell you, in fact, the same story, same as the one that I've just told, but in a different language. Because instead of trying to delete this root edge, we could try to contract it. That's somehow the dual operation. And again, there's two cases. Maybe this root edge is a loop, in which case you can't really contract it, but you see that you have two smaller maps, one on the left, one on the right, that you could glue, and you could go backwards. And otherwise, the root edge is not a loop, and then you can contract it. That is, you shrink it so as to merge these two vertices here. And as you can expect, because in fact I'm doing the same operation as before, but on a dual map, we have the same phenomenon here. Namely, this smaller map here is obtained several times, and more precisely, if the root vertex, now the root vertex, not the root face, has degree d, then it comes from the contraction of the root edge in d plus 1 different maps. And so we could introduce the number now twiddle of NE, of rooted maps having n edges and root degree E, and we would write exactly the same recurrence relation as before, which is completely normal because we are really doing the same operation but on the dual of the original map. So you may wonder why essentially I'm telling you twice the same story, and the reason for that is lies in the next problem that I want to address, where now we'd like to count colored maps. So think first of maps equipped with a proper hue coloring. So it is known that the number of Q colorings of a given graph or map is in fact a polynomial in Q, which is called the chromatic polynomial, and which can be computed very nicely in a recursive way. And this identity, which is essentially proved here, I mean, it's very easy to prove, tells you that the number of Q colorings of M is the difference between the number of colorings of M where you have deleted a given edge, E, and the number of colorings of M where you have contracted the same edge. So I use this notation. It's probably not very standard, but that's what it means. And really that's very easy to prove. So you get here a taste that counting colored maps will involve both deletions and contractions of edges, and hence maybe will force us to keep track not only of the size of the map, but also of each of these two additional parameters that we had before, that is the degree of the outer face and the degree of the root vertex. So we're going to do that not for the chromatic polynomial, but as I told you, we are interested in all colorings now. But we are going, I mean, if I have k vertices, the number of colorings is q to the b, so that would be a very easy counting problem. But we want to weight these colorings with new variable nu to the number of monochromatic edges. So we introduce what I call here the Potts polynomial. So this is named after the Potts model in statistical physics. So this polynomial is the sum over all colorings of the vertices in Q colors of nu to the number of monochromatic edges. And so in particular, if nu is 0, then the only coloring that survive here are the proper colorings. And so at nu equals 0, I get back this chromatic polynomial. So let's take here a very small example, a map with just one edge, and compute the Potts polynomial. So if I want the edge to be monochromatic, that is to have a weight nu, and there's just q ways of choosing the color. So this gives this term. And the number of proper colorings is q times q minus 1. That's an example. Okay, and so this Potts polynomial, it's very easy to see that it satisfies a very similar recursion, generalizing the one for the chromatic polynomial. So again, what I'm heading to is that I'm trying to tell you that if we want to write a recurrence relation or functional equation, then we will have to keep track of two additional parameters: degree of the outer face, degree of the root vertex. So let's do that now. So I introduced this, my third series. We had A for trees, B for uncolored maps, and now there's C for colored maps. And so this series C is the sum over all Q colored maps of T to the edge number, it's the size, nu to the number of monochromatic edges, the bad edges in a sense, like this one. And then we have our two additional variables and statistics, the degree of the root vertex, here 3, and the degree of the root face, here 6, hence the y6. And then I won't give any details, but one can indeed write a differential equation defining this power series. And as you can now expect, I hope, you will see in this equation discrete derivatives with respect to x and with respect to y. So that's the new point in this equation. So I tend to call it now a discrete PDE because there are derivatives with respect to these two variables. And this equation was written by, guess who? Tat. And then it slept for 40 years, essentially, until my colleague Olivier and I tried to wake it up. Okay, so just a little remark here. So in his paper, this is the paper in 71 where Tutte wrote essentially this equation. He was not playing with this Potts polynomial. He was playing with what is now called the Tutte polynomial, which is defined in the way it's defined, and which is closely related to the Potts polynomial by essentially a change of variable. So the equation he got was a bit nicer because when you take a map and replace it by its dual, then in the Tutte polynomial, the variables mu and nu are exchanged. So he had an equation that was nicely symmetric in mu and nu, which is not the case of others, but it's exactly the same problem. Okay, so far we've split maps into smaller pieces, and this has led us to 3 equations, a nice polynomial equation which we've solved for trees, a discrete differential equation for planar maps, and a discrete PDE for colored maps. And before I tell you about trying to solve these beasts, I want to tell you that these decompositions, they are so basic and naive in a sense that they are also very robust. And you can address many families of maps using the same ideas. So for instance, I've taken 2 examples here. If you want to count plane triangulations, that is, you want now every finite face, every bounded face to have degree 3, you end up with a discrete differential equation, where now the derivative is taken around 0 rather than 1. And here, that's another equation that Tutte wrote. If you want to count again triangulations, like this one, which are properly Q-colored, so there's no parameter nu for monochromatic edges, you get also a discrete PDE, where now the derivatives are taken around x equals 1, y equals 0. And one could produce more equations of this type. Okay, so question, what are we going to do with these equations? Well, maybe nothing. After all, maybe we could say that we've characterized the numbers we were interested in, and maybe we can stop here. And after all, this equation, whether one likes it or not, allows you to compute the coefficients, that is the number of Q-colored maps in polynomial time, which is already something. There's tons of counting problems for which I would be extremely proud to come with a polynomial time algorithm to produce coefficients. Think of, I don't know, counting self-avoiding walks on a lattice. No one knows how to do that in polynomial time. Okay, so maybe we should be happy. On the other hand, we were really interested in the series where x and 1 are 1. That is, we don't record the degree of the root face and the degree of the root vertex. And it's a bit annoying when you are interested in this series not to have some intrinsic characterization of this series. That is, to have to go through these additional two variables. And also you may think maybe if we could characterize this series, then we could work out certain asymptotic results on a number of large maps, maybe phase transitions, since we are not far from statistical physics models. So maybe we're not that happy after all. And in addition to that, I would say that experience and past results make us greedier. Because if we return to this discrete differential equation, that was our second equation, the one that counts planar maps, well, you could say it's nice, it's a closed form characterization, but in fact, it is known that its solution, and in particular the series B of 1, where every map contributes t to the h number, that is the series we really want, this is a simple algebraic series with a nice expression and nice coefficients. So when you see that, I mean, one is certainly convinced that this is a much nicer result than this equation. So we cannot stop at such equations. So maybe returning to this one, maybe after all, this series as well satisfies a polynomial equation. Maybe it's an algebraic series, and then we would like to know it. And more generally, when we have in enumerative combinatorics, and we often have functional equations of a not so usual type, we always try to decide whether its solution fits in a certain hierarchy of formal power series, a very classical formal power series, satisfying functional equations that are much more classical than the one we have. So let me describe this hierarchy here. So the simplest possible power series, they are the rational series, like this one. And then comes a slightly more general class, the class of algebraic series, like the one for trees, which are those that satisfy a polynomial equation. Now we know that planar maps also satisfy a polynomial equation, so they are in my second drawer. Then comes an even larger class, the class of D-finite series, satisfying a linear differential equation with polynomial coefficients. And they include algebraic series. And then in this big drawer are D-algebraic series, those that satisfy a polynomial differential equation, but maybe not linear. And of course, not every series fits in this chest of drawers, so you have a big black cloud of series which you cannot put in the drawers. So these are definitions for one variable series, but there are counterparts for series in several variables. So returning to our collection of three equations, well, this one is algebraic, it's obvious. This one we've seen, I've told you that the solution is algebraic. What about this one? So this result, that is the algebraicity of this series B, which solves a discrete differential equation, is in fact an instance of a very general phenomenon that we proved some years ago with the Arnaugian. And this result tells you the following. If you have a series in one main variable t and one additional variable x, that satisfies a discrete differential equation of a polynomial type. And by this, I mean that you have the polynomial in the variables, the series, and then this delta x of A is the discrete derivative. Here I've taken it at 0, it could be at any other point. And you can iterate this discrete derivative, we'll see an example later. And you take a polynomial in all those quantities, you say it's 0, and you assume that the equation is proper, which means essentially that it has a unique solution in a set of formal power series. Well, then this series A is in fact algebraic. And so the first result of that type was proved by Brown, who was, I think, a student of Tutte in Toronto, who designed something that's now called the quadratic method that applies to polynomials of degree 2 in A with, I think, just one derivative at first order. And then there's another example for a linear equation later in Knud's book, The Art of Computer Programming. But in fact, this is a very general phenomenon. And embarrassingly, a few years after we wrote that, I learned that it is a special case of a hard theorem in algebra, which is a kind of Artin approximation theorem, which is due to Popescu, and then apparently the proof was not completely convincing, and the result was reproved later by Swan. But so I must say that I don't understand those papers. There's too much algebra for me. But one advantage of our approach is that it is effective. That is, if you take that equation for plane maps and type 2 lines of maple, you obtain for B of 1 the series we're interested in, this quadratic equation. And here's a more complex equation for some other maps called constellations, where you see we have a cubic equation, and maybe the interesting object here is, so now the differences are taken at 1. So this is the second order discrete derivative, A of x minus the first terms in its Taylor expansion divided by x minus 1 squared. And for this one, A of 1 is the cubic. Okay, so much for discrete ordinary differential equations. They are in a sense simple because their solutions are always algebraic. Now, what about these discrete PDEs? That is where we had discrete derivatives with respect to 2 variables, which arise when you count colored maps. Well, this is a completely different story, and I will illustrate this by a preview of some things that I'll tell at the end of my talk. So here you have 4 equations, discrete PDEs, so which involve derivatives in x and in y, with still the same definition as before. And you see they are very simple. In fact, they are the simplest possible discrete PDEs you could dream of. And the only thing that changes is this blue coefficient. And here also there's a y that comes here that you didn't have in the previous equations. Well, I claim that the solution of this one is algebraic, satisfies a polynomial equation. The next one is definite linear differential equation, but not algebraic. This one, you can feel what I'm saying. It's not definite, but still you have a polynomial differential equation. And this one sits in the big black cloud that I had on my hierarchy. Okay, so this tells you that the thing is richer and certainly very interesting. But let's go back a few years ago when Olivier Bernardi and I decided to try to do something with this equation that had been sleeping for 40 years. So we had we had no particular bright and new idea to address this. What we did, what we wanted to do, was to follow Tutte's steps, of course. Because I told you that after having written this big beast, Tutte wrote this slightly simpler discrete PDE for properly Q-colored triangulations in 73. And then he spent 10 papers and about as many years, I think, trying to solve this single equation. So this is the series of papers. So you see certain titles are not especially illuminating. This lambda, that's my Q, that's the number of colors. But then the last one has two important words in the title, differential equations. And what he finally produced in this final paper is a differential equation for the series he was really interested in, which is a specialization at x equals 1, y equals 0. So t of 1, 0, he proved that, and he gave an explicit differential equation for t of 1, 0 after 10 years of struggling with this equation. And I think that he found this series of papers important, and I fully agree it's full of invention. I don't know how he imagined that. Because 10 years later, again, he wrote a survey on the solution of this equation, and this is where we started from. So let me show you this, show you a description, now a modern description of his results. So a first group of results in these papers is that he proves that for Q of a very special form, 2 plus 2 cos 2 pi over m for some integer m, then for those values, he was able to, in a sense, to eliminate the variable x. That is to obtain an equation for t of 1y, which we would now call a discrete differential equation in y. So now we know that all these equations have algebraic solutions, but at that time this was not known. And then he proved first for these values of q and then for generic q that this series t of 1, 0, the interesting specialization of t, satisfies a certain non-linear differential equation. So you see it is degree 2 and order 2 as well, with a 4 minus q here. Isn't that nice? 4 minus q. Q being the number of colors. So maybe you don't like this differential equation, so I will show you the corresponding recurrence relation on the number of properly colored planar triangulations. So this is again the differential equation, but what it really means is this. That is, if you call h of n the number of q-colored triangulations, properly q-colored, having n vertices, then there's I think a very nice recurrence relation for these numbers, involving a linear term here with a factor q minus 4. So when you have q colors, something happens. You have no linear term. And then a kind of convolution that looks a little bit like what we had for trees. And the point here is that since Tutte's solution of this problem, no one has been able to reprove in any other simpler way this recurrence relation, which looks for a combinatorialist. It looks like something that one should try to explain. Say, maybe when you have 4 colors, you have here a sum of positive terms. There should be a combinatorial explanation, but at the moment there's not. Okay, so with Olivier, we got back to this more complicated problem involving general Q colorings and then this additional variable nu, counting the number of monochromatic edges. And we established results that completely parallel the results that Tutte had obtained. So for a certain family of values of Q, including 2 colors and 3 colors, we were able to characterize this specialization of the series intrinsically, that is without using X, by a discrete ordinary differential equation in Y, and to derive from that now that for these values of Q, the generating function of colored maps is an algebraic function. And then for generic Q, then we could write a system this time of differential equations that defines the series C of 1, 1. So I won't say much more about this result. I will just show you a special case that I find nice. That is when you have 3 colors. And you take nu equals 0, meaning that you want to count just proper 3 colorings. So here is a map, one of the maps that you want to count, properly colored in 3 colors. Well, our theorem tells that the corresponding series at 1, 1 has to be an algebraic function. And one way of describing it is to introduce the series A that satisfies here a quartic equation. And then the series of maps is some rational function in A. And again, this problem that is rather, I think, appealing to people in combinatorial enumeration with this simple series that resembles a bit a series of trees, has only this very long proof that we designed with Olivier Bernat. Okay, so let me check my watch. Yeah. So to finish, I would like to give you an idea. I would like to do some mathematics. I would like to give you an idea of one important ingredient in Tutte's solution of these partial discrete PDs, or PDE. And I will illustrate it and explain it not on these complicated map equations, but on the simpler discrete PDEs that you've seen earlier as a preview. And these equations, they arise in a different category of counting problems, namely when you count walks, lattice walks like this one, that are confined to stay in the first quadrant of the plane, in the non-negative quadrant. So here is one of these problems. Say I take these 3 steps, north, east, west, south. I start at 0. And so there's, with n steps, I can do 3 to the n paths. But I would like to count those that never leave this first quadrant. And this is a problem that was studied and solved by someone named Germain Créveras, who is almost a perfect contemporary of Tutte. I don't know whether they ever met, but I'm sure that if Tutte had seen this problem, he would have solved it in the 60s or 70s, having solved his problem of colored maps in a much faster way than Germain Créveras did. So the Créveras paper is 100 pages long to count these rules. So I want to present you the kind of proof that maybe Tutte would have designed, and then this will tell you what are Tutte's invariants. Before that, I should warn you that, of course, one calls, for instance, the chromatic polynomial a graph invariant, but these invariants are not at all graph invariants. That's a different notion. Okay, so the first thing I want to do is to explain why discrete PDEs arise when you count walks in a quadrant. And this is easy to understand. So I start anew with a new counting problem, and I call Qij of n the number of walks of length n that start at 0, 0, and at ij consist of n steps, this I said, and never leave the quadrant. And I put all these numbers in a big generating function with, as before, my size variable is t, and x and y record the coordinates of the endpoint. And I'm going, as for maps, to give a recursive description of these walks, in fact, obtained by just deleting the last step. And this will give me a functional equation, a discrete PD. So let's do that. So this equation here tells you that, well, a quadrant walk is either reduced to a starting point or is obtained by taking a shorter walk, maybe the black walk, and adding a northeast step. So this increases the length by 1 and also the coordinates, abscissa and ordinate of the endpoint. This gives this factor. Then maybe there's the walks that end with a west step, and these ones, I construct them by taking a shorter walk and adding a west step, which increases the length but decreases by 1 the final abscissa. But this I cannot do, this construction I cannot do if I start from a walk of length n-1 that ends already on the y-axis. And this is why you see here this difference of series, because q of 0y, if I specialize x to 0, what I get here is precisely the generating function of walks that end at abscissa 0, that is on the y-axis. So here, these divided differences, they have a natural combinatorial interpretations, because, or at least a difference, because this is the class of walks that end at a positive abscissa and to which I can concatenate a west step. And here you have a completely symmetric case. So really, I would say that these quadrant walk problems, they are the ones that give the simplest and most natural discrete PDEs. So now we can play a bit with the equations. So I've grouped together all the q of x, y's. And so here I have a certain polynomial, which I call the kernel. And on the right-hand side, I have these two specializations of my main series. Okay, and what I want to do now is to tell you how I think Tutte would have derived from the equation that q of xy is algebraic.
Miriam?
Wait, yeah?
If you could finish in the next 5 minutes, that would leave a little bit of time for questions.
Yeah. Yeah, I try to do that. Okay, so where was I? Okay, so here I will have this shortcut R and S. You see the right-hand side is nicely split into a series in X plus a series in Y. So the first thing is to look at this kernel and look at it's a quadratic polynomial in Y. So it has two roots, which are series in T with coefficients that are polynomials in, polynomials or Laurent polynomials in X. Never mind these details. You can cancel by an appropriate choice of Y, in fact, by two choices. You can cancel the kernel, and then the planar is 0, and the right-hand side is 0 as well. So let's do that. We get 4 equations. 2 of them tell you that the kernel vanishes for each of these 2 series. And since the left-hand side vanishes, then the right-hand side has to vanish too. So here are again the 4 equations. Now I'm going to to extract from them two equations that involve neither x nor r of x. But I'm happy having the other unknowns. So first I can eliminate x between these two, and look at that. If I eliminate x between the two kernel equations, I can write the resulting identity in this form. A function of y0, the first root of the kernel, is equal to the same function at y1. And this function of y and t is what Tutte would have called an invariant. It takes the same value at the two roots of the kernel. And that's not the end of the story, because then you can also eliminate easily r between these two equations, and then eliminate x again using this. And what you get is that there is a second invariant. Namely, if I define J to be S of Y, S is essentially my series Q of 0, 1, plus 1 over Y. Well, this series as well takes the same value at Y0 and Y1. This would not necessarily be the case if I had different steps. So I have these two invariants. One is explicit and rational. The other is a Q invariant. It involves the series Q. What can I do? Well, then there's a lemma that's simple to prove that tells you that, in fact, this invariant, which has a double pole at 0, has to be a polynomial in the other one, with coefficients that are series in T. And this polynomial, well, it has to start with the T times J squared to kill this double pole. And you can write, in fact, the resulting identity. So I is T times J squared minus J minus 2T squared Q00. So you have combined these two invariants using this lemma that tells you that, in fact, they have to be related. And what you obtain here in these guys is a discrete differential equation for Q of y0. And now we know that the solution has to be algebraic. And that's the end. So that's the solution, and that's the very nice numbers that Creveras obtained in 65. And then, so this is a very small part of a story that's been going on for 20 years, where people have tried to study it in a systematic way, quadrant walks with small steps. And there's 79 distinct steps to study. And some have rational invariants, some have Q invariants. And the nice conclusion of that is that, in fact, the classification of the corresponding quadrant problems and of their generating functions completely parallels the classification according to whether these step sets have rational invariants or not, Q invariants or not. So, for instance, what I mean here is that the series is definite if and only if you have a rational invariant, and algebraic if and only if, in addition, you have an invariant involving Q, like the Creveras model here. So this is a long story, but I think that it shows that this wonderful notion of invariance that designed in this mysterious series of papers is promised to a new life. And I'll stop here. Thank you.
Yeah, thank you, Mary, for a great talk. Are there questions? People online can feel free to ask them. Anyone in person, the microphone doesn't have that large a range, so you can either speak really loudly or come up and ask a question.
I was just wondering if there's an explicit formulation of the Polynomial conjecture in terms of the generating series of Q-colored maps.
Did you hear that, Miri?
An explicit expression for?
The four-color conjectural theorem in terms of the generating series of Q-colored maps.
I'm sorry, the sound is very bad. Maybe Steve, could you repeat that slowly, please?
Is there an explicit reformulation of the four-color conjectural theorem in terms of the generating series of Q-colored maps?
The four-color theorem. So, not that I know. It's often said in our community that the reason why Tutte started to count first maps and then colored maps is a motivation. It was motivated by the four-color then conjecture. I must say that I've never understood how this could be true. The only explanations I've heard is that, so we are not counting for colorable planar maps, we are counting for colored maps. And the only explanation that I heard once is that maybe if some planar maps were not for colorable, this after some point, after some size, many maps would contain the bad maps and hence not be for colorable, and that maybe this would be visible at some asymptotic level on the number of such colored maps as well. There will be very few four colored maps if some planar maps were not colorable. But I've never seen a rigorous version of this, so I don't know.
Okay, other questions? I guess, so you've worked on two different problems that, use discrete differential equations, planar maps and lattice paths. Did you just come to both of these independently, or was there something about one of them that also attracted you about the other, and that's what causes them to have similar equations?
No, I'm not sure I remember. I think at first it was independent. So I had been interested. Yeah, I think it's all started independently. So I was fascinated by this series of papers by Tutte and the survey, which I had never been brave enough to read, I must say. And it was Olivier who read it as a master student. And then it took many years before we started to apply Tutte's idea to colored maps. And then in parallel, I was working also at the beginning of this century on some instances of these lattice walk problems, in particular the Creveras one. And it's only, so I solved such equations using different techniques without invariance. And there was a hint in Olivier Bernardi's thesis in 2006. I think he had shown how you could solve Creveras walks with invariance. And then we had tried to do it for another, for this model, which was, there were very nice conjectures, and then a proof that the series was algebraic. And we had tried to prove it using invariance, and we had failed for years. And then much later, there was this discussion with Kylian Rachel. I mentioned these attempts, and at that time he told us that maybe instead of one invariant between being a polynomial in the other, then maybe it could be a rational function in the other. It was as simple as that, and this was the case. And since that, we've understood much more. So there is something a bit misleading in this picture. So for the moment, what we can prove using invariance is the algebraicity results and the de-algebraicity results. I have some hopes for this one. But for instance, these hard results, they involve something that's completely different, namely Galois theory of differential equations. So you could think, I mean, it's not a coincidence that these classifications of invariance and of the nature of the series match. But for instance, at the moment, there's no proof of definiteness that uses the Q invariant. So yeah, so for me, it's been two parallel stories, and using invariance in walks has come rather late, rather recently.
Okay, great. I think we're out of time, so let's thank Mireille again. Interesting results and a great summary of Tut's work on planar maps. So next week we have Walla Mercy from Waterloo, who will be speaking about her research. And it's not clear, it might be in person or it might be online, but either way, we'll have a hybrid setup again where people can watch either in person or online. So thanks everyone, and see you next week.
Thank you.
Thanks, Mary. Sorry for any sound problems that might have come up. Still working out the setup.